Hello everyone, I am excited to present you our work Pose-disentangled contrastive learning for self-supervised facial representation. Our code is available on the GitHub. Our propose a novel contrastive learning framework, namely Pose-disentangled contrastive learning, termed PCL for general self-supervised facial representation. The PCL introduced two modules, Pose-disentangled decoder (PDD) and pose-related contrastive learning scheme. The PDD disentangles the pose-related features from the face-aware features. The pose-related contrastive learning learns pose-related information. We conducted linear evaluation on four challenging downstream facial understanding tasks, such as facial expression recognition, face recognition, AU detection, and head pose estimation. Most of existing datasets just can be used in one special facial-related task, such as facial expression recognition, AU detection, or face identification. Labeling a face with multitask annotation is a time-costly process. In the real world, there are lots of unlabeled facial data. The work focuses on how to use unlabeled face data to learn general face representation for different face-related emotion tasks. Existing contrastive learning, such as SimClear, can be used to perform face understanding on large-scale unlabeled dataset. However, it tends to learn pose-invariant features that cannot depict the pose details of faces. Nevertheless, poses are one significant consideration for facial understanding. For example, as shown in the right figure, a person tends to lower their head when they feel sad. To tackle the above limitation of CL, we propose a novel pose-disentangled contrastive learning PCL method, which disentangled the learning on pose-related features and pose-unrelated facial features for CL-based self-supervised facial representation learning on large-scale unlabeled data. This is the training pipeline of the PCL. Our PCL mainly consists of two novel modules, such as a pose-disentangled decoder (PDD) and a pose-related contrastive learning scheme. Taking a face image as input, the PDD first employs a backbone network like ResNet to extract general facial features and then attaches to subnets to produce separate pose-related features and pose-unrelated facial features. To train the PDD properly, we reconstruct the face through the combination of the two losses. For example, a disentangled objective and an orthogonalizing regulatio. With the disentangled pose-related features, we further devise a pose-related contrastive learning to enable effective self-supervised learning on pose information, suppressing the side effects of pose-invariant features. For example, for the same face image, we apply pose transformation and image transformation to it separately. Then we use backbone and nonlinear function GP to extract the pose-related features. Finally, we consider the same image pairs containing different poses as negative pairs and the same image with containing the same pose as positive pairs for contrastive learning on the pose. This is the pose-related contrastive loss. Together with pose-related contrastive learning, we employ face contrastive learning on the pose-unrelated facial features like this. It is a normal CL procedures. This is the face contrastive loss. The pose-related contrastive learning and face-related contrastive learning are trained in a dynamic multitask learning manner. We used the DWA to learn the multitask ways to better balance the pose and face tasks during training. Our PCL can be well generalized to several downstream tasks, such as facial expression recognition for AU detection, facial recognition, as well as head pose estimation. Given the trained model, we investigated the learned facial feature by evaluating the performance of its applications on facial expression recognition and facial recognition. The quantitative results shown in table demonstrate that our proposed method is able to provide superior performance with respect to other methods. This is the evaluation for head pose estimation, including head pose classification and regression. Our PCL achieved the lowest mean absolute error MAE of 12.36 on a FLW and the best accuracy on BU3 DFE, outperforming the other self-supervised methods. This is facial AU detection task. Our PCL achieved the SOTA performance on several challenging downstream facial understanding tasks, even obtained results comparable to the full supervised methods. This is the ablation results of the gradual addition of different components into the baseline. The results verifying that each module can help improve CL-based self-supervised facial representation performance. In order to demonstrate that pose-related information can be complementary to face information, we use different facial features perform linear evaluation on 3 facial tasks. The left figure shows the disentangled pose-related and pose-unrelated facial features, and the right show the reconstructed faces with the disentangled features. The results demonstrate that our method can effectively separate pose-related features from pose-unrelated facial features. This figure shows the features learned by the sim clear and our PCL respectively. Obviously, our PCL can learn better distinguished features. In general, the major contributions of this work are summarized as follows. The PCL is a novel pose-disentangled contrastive learning framework. The PCL designed a pose-disentangled decoder to separate the face-aware features obtained from the backbone into pose-related and pose-unrelated facial features. The PCL introduced a pose-related contrastive learning scheme for pose-related feature learning. The PCL can be well generalized to several downstream tasks, such as facial expression recognition, facial AU detection, facial recognition, and head pose estimation. Thanks for your watching.